So my name is Strzebonski. I'm a symbolic algorithm developer at Wolfram Research. I'll be presenting and talk about symbolic computing with geometric regions. It's a joint work with my son Pavel, but he has classes, so he couldn't present the talk. So I will be presenting the talk. So let's see. We have many regions, many region types in Mathematica. So the basic categories are special or basic regions, formula regions, derived regions, and mesh regions. And the region type I'll be concentrating on in this part of my talk is basic regions. So what are basic regions? So basic regions are some named geometric objects. Is it large enough, or should I make it larger? OK. So here they are. So regions are some named geometric regions that we have built in that are commonly used. So we have 36 of them. Right now, there are 36 special region types. And in version 10.3, we introduced 10 new special regions types. Here are they listed. Roger has already shown them. So I'll just scroll through all the region types. The basic idea is that we have many of those. And so how do we do symbolic computation with regions? So what do we want to compute? We can compute region properties. So here are the functions that compute properties. Region membership, then the dimension properties, measure properties, distance properties, and deciding whether region is bounded and computing region bounds. So here are the various properties of regions that we might want to compute. We can use region as input to symbolic computation functions. So here are the functions that take regions as an input. So the equation solvers, optimization functions, integrations, the assumption mechanism, all can take regions as input. Now, so what's the general method? So this, the most general method of handling a problem involving a region is to find a system of equations and inequalities that describes the region, and then use the symbolic computation methods that solve the problem written in terms of equations and inequalities. So it would be solving equations and inequalities, quantifier elimination, or constraint optimization. And the most general method that we use there is the cylindrical algebraic decomposition algorithm. So in principle, we can compute anything about semi-algebraic regions. These regions that can be described by polynomial equations and inequalities. But the algorithm we are using there is general, but it's slow. And also in general, if we have derived regions like region union, region intersection, transformed region, those do not auto-simplify. In general, we cannot do anything with, we cannot represent arbitrary transformation of an arbitrary region as a built-in region. However, if we have special regions, that's a different case. We may be able to represent derived region in terms of another special region. So here, for basic regions, if we are thinking just about the 36 special region types that we have, we often have closed form formulas for computing region properties, or for integration over the region, or we can auto-simplify regions constructed with basic regions. And those those formulas usually match. Using the formulas for special methods is usually much faster than using the general method. So for instance, here's the very simple example. So we have a ball that's described using equations in inequalities. So if we write this as an implicit region, that's what will happen. Here we are using the cylindrical algebraic composition to decompose the ball into cylindrical pieces, and then we use integration to compute the volume, and in almost 10 seconds we have the volume of the three-dimensional ball. But of course, if you just request volume of three-dimensional ball, then you get it immediately. This time here is loading the package. Second time around, it probably would be 0. Well, I don't think we can made it work with symbolic n, but you can do volume. Volume is a 3D volume. So it's infinite for 9-dimensional ball. For region measure, it's 0 time, and we got the answer. Because we have the formula for n-dimensional, for volume of, or measure of n-dimensional ball, so that's what. Of course, if I tried integration, that would probably take a very long time.
I will give you formulas for it.
Okay, we have. That's why we got the result. So, how is the implementation of specialized method? How is it done? So basically, we have collection of formulas or special case algorithms for computing with basic regions. So we can compute properties of special regions, operations on basic regions, and relations between basic regions. So what are the properties? So here's a rather long list. We have 20 properties of basic regions and 12 properties of basic region boundaries, because a boundary of a basic region may not be a named basic region, but we still can have something like surface of an ellipsoid. We know the formula for that, so we can store this. And surface of an ellipsoid would be region boundary of ellipsoid, because we don't have a name for it. So here are the 20 properties that we are storing. Some of them correspond directly to functions that we have, like region measure. Others do not, like parametric description or injective parametric description that's useful for integrate, but there is no direct function for it. So we are also storing some properties of special regions that might come useful in computation with them. And we store 12 properties of boundary of the region. Region operations. So right now we are storing 2 binary operations: intersection of regions. So intersection of 2 special regions may give a special region, and product. So Cartesian product of 2 special regions may give a special regions. We can take Cartesian product of a disk with an interval, and we'll get a cylinder, for instance. And we have 2 unary operations, image and pre-image, which will store the computation of transformed region and inverse transformed region of a special region. Again, they may be expressible as a special region. Currently, we have the special methods for computing linear or linear fractional transformations of regions. For higher dimensionals, unfortunately, we have to go to the general method. And region relations, right now we don't have top-level functions, but we will have top-level functions computing region relations, but we are already storing subset, disjoint, and equal relations, so we can tell whether 2 special regions are disjoint. And it will, again, it can help in computation with those special regions. Like if you have intersection of 2 regions that are disjoint, then it's empty, nothing to compute. Or integration over a union of 2 disjoint regions can be, we can integrate separately over each region. Okay, and we have integration rules. So right now we have specialized integration rules for 33 basic and derived regions. So we can have code for fast integration of polynomials. So for many regions, we just have closed form formula for what is the integral of a polynomial over this region. And we have some nice parameterization stored with special regions so that integrate has an easier job, because the general method, if we go to cylindrical decomposition, we get parameterization that uses algebraic functions as integration bounds, which may not necessarily be what integrate can deal the best with. So for instance, for many cases, trigonometric parameterization is much easier for integrate to handle. And here's some statistics of implementation. So that's something what my son was working on. We have 17,000 lines of mathematical code implementing all types of properties and special formulas. And we have 1,752 different formulas and special cases. So here are some examples. So auto-simplification of Boolean operations. So in general, Boolean operations stay unevaluated, but if we are working with special regions, like we intersect half plane with stadium shape, we get a disk segment. Here is a picture of it. Or no, I have to first evaluate something here. Oh, this was the picture. What happened? Oh, OK. I evaluated out of order. I use the same names everywhere, so I have to really evaluate it in the correct order. So here, this is stadium shape intersected with half plane. And we get disk segment. And that's another example, which I evaluated first. We intersect cuboid on infinite plane. We get a polygon, which is hexagon, I believe, here. And here's the picture. So this basically we have for pairs of special regions, we have a rule that computes the intersection. And here are some examples using region relation rules. For instance, we have here union of disk and polygon, and it turns out to be a polygon because we can decide that the disk is already included in the polygon. So we can auto-simplify. This seems trivial, but for further computation, it's really much easier to deal with a single regular polygon instead of a region union. And here is ellipsoid and cuboid, and we get back an ellipsoid. So we compute difference of ellipsoid and cuboid, and we get back ellipsoid, meaning that they most probably were disjoint. They were disjoint, and we were able to figure this out and auto-simplify region difference. So as I said, auto-simplification makes further computation with the region much easier. So here we compute the distance from region difference of these two regions, which evaluates to ellipsoid, and we can use formula for distance from ellipsoid in this case, and it comes back immediately. And this one I probably shouldn't evaluate. So this here, it wasn't that bad. So we force it to use equations and inequalities by wrapping everything in implicit region and taking the region membership formula. And now the same problem takes 4 seconds to solve. So it's what? Well, here I have it computed 294 times slower. OK, so here's auto-simplification of region product. So we have product of disk and an interval, and it comes back as a cylinder. And again, we can show that it makes further computation faster. We can integrate a polynomial over the cylinder, and we have formula for it. So again, it takes no time. I think this 15 milliseconds is the lowest time this computer shows for some reason. So, and if we use the general method and do the same integration, then OK, it was 3 seconds, not so bad. But it's still a few hundred times slower. So auto-simplification of a transformed region. So here we have ball. We transform it using an affine transform, and the result is an ellipsoid. And we can compute volume. And again, it comes back immediately because we have formula for volume of an ellipsoid. If we used the general method instead, it would take 10 seconds to compute. Now, distance properties. So for instance, like let's take the capsule shape. And well, there's a little demo. So we have signed distance to this capsule shape. And it works fast enough that I can actually show it on the manipulate demo. So what does it take? We need to compute signed region distance, and we have to compute region nearest to the region boundary. So we have to have the formula involving the boundary of a region. The region boundary does not simplify for ellipsoid, but we still have region nearest formula for distance to it. And this is very fast. And again, if we use the general method for signed distance computation, it would take 20 seconds for one point. And there I was just using manipulate, so each point was computed in a fraction of a second in real time. Oh, here are some. OK, so yeah. For 0 seconds and 0 seconds distance and signed distance for using the formulas for one special point. And yeah, if we wanted to compute nearest point on the boundary, which is the one that we need to mark this point and be able to draw a line between them, that takes forever. Well, actually, it takes a long time and then fails because we cannot, in the current version of Mathematica, we cannot even compute equation inequality description of a boundary of an arbitrary semi-algebraic set in R3. In the next version, we will be able to do it, so at least it won't fail, but it will be slower if we use the general method. OK, measure properties. So we have 5D ellipsoid, and we compute measure, takes 0 time because we have formula. And if we use the general method, it would take 87 seconds. Integration over the ellipsoid. And we have the formula for region measure of region boundary of ellipsoid, but this formula actually exists only for up to dimension 3. So for higher dimensional ellipsoids, there is no formula for the boundary. This already uses two elliptic functions to get the 3-dimensional ellipsoid. And so this was using, actually wasn't that slow, but it's just numerical. So we can use numerical integration to compute measure of a boundary of ellipsoid in higher dimensions even. But it's still somewhat slow, but it's not terribly slow, and we get an answer, at least the numerical approximation of it, while there is no formula. So that's the only way to do it. Here is some centroid examples. So we have disk segments, again, 0 time computation of centroid, because we have formula for it. Here's what it looks like, the disk segment and the centroid. And using general methods, if we compute the same centroid, it takes 2 seconds and returns something really large, because it's 2 integrations divided, so that's complicated. And the integration, so here we compute integral over a cone. Again, integral of a polynomial over a cone, and it's immediate because we have a formula for computing such integrals. The general integration method fails because, while we can get the algebraic parameterization of the cone, integrate cannot deal with the algebraic functions we get there as the description, and so this failed. We could do numeric integration using the general methods, but not exact integration. And here is something where we compute an integral of a polynomial over a 5D simplex. Again, it's almost immediate. There is some noticeable time, 31 milliseconds. But the general integration didn't finish overnight. So in principle, it should do it because it's all linear, but it takes a long time. And here we compute integral of a polynomial over a unit ball in 7 dimensions, again, fast. And the general method is much slower, which means that it did finish. Yeah, it's 268 seconds. So that's the first part of my talk. The second part is a demo of some new features that are coming in a future version. So we have this in the development version. And so the design of what I'm showing will change, but I'll just show what will be possible to do, even if the functions will be named differently. So we have, in the new version, we have function for computing topological operations on semi-algebraic regions. So we can take closure. Oh, magnify. Oh, OK. So we can take closure or connected component or interior, this kind of stuff. So here is a semi-algebraic set. The region cylindrical decomposition represents is a semi-algebraic region. I don't know if this particular representation will survive, but that's what it is right now. And here's the picture of the region using semi-algebraic region plot. I'm using, again, this unofficial function because it shows what parts of the boundary are in, what parts of the boundary are out. So this particular region has the blue parts of the boundary are in, the gray parts of the boundary are out. So they do not belong to the set. So now I can compute the closure of the region. And the picture looks like this. So all parts of the boundary are now blue.
Shouldn't the closure have a nose?
And the interior has lost the antennae. And the next one is boundary. Again, now it says the dimension is 1, which is good. It should be 1. And here's the picture. So there's the boundary. And the interior closure, so it's closure of the interior. So we should lose the antennae, but we should get a closed set. And I won't evaluate because it takes about 10 seconds to compute the picture. So here's the picture. And the last one is connected components. So here it is. It has 3 components, and here is the picture. There are the eyes are not connected. So here we got this. And one thing I added yesterday, so there was a talk about Gaussian decomposition. So we can now compute in one line a Gaussian decomposition of a 2D curve. So here's the curve. And so it's the real part of this 7th degree polynomial. And here are the components, and here what the picture looks like. So the idea of the composition is that we take components of where the polynomial is positive. So these are the blue parts. Then we take the boundary of each component. And then we take components of the boundary, so that this part, and this part, there are 3 different curves, even though they are the boundary of the same thing, same blue area. So quick application of this thing. So that was all I had. Thank you.